Sounds good. Hi, everyone. Thanks for the opportunity to talk about this work at Quantum Meets. My name's Joseph Slote. I'm a postdoc at the University of Washington, working on complexity theory and learning and so on. Yeah, so this is actually, I'll be talking on a follow-up to a paper that's out. I'll talk about them kind of together. But the goal here is this state certification where you have an unknown state and you want to make sure it's a state that you were supposed to create, which is a kind of a basic task in quantum engineering and science. So these two works are with my lovely collaborators here. Okay, so let's get into the task and see what's known and not known and so on. Do please interrupt with questions. So, okay. Yeah, so the idea is you have some process that generates copies of some state, and you can imagine having some control over the process, so it's not completely adversarial. It is copies of a state row. It just may not be the state that you wanted. And so the idea is you want to certify that it is actually the state that you wanted, or if it's far from it. So exactly this. And we're going to assume the target state is pure. Things are roughly still possible when it's slightly mixed, but that's outside of the scope of this project. And the idea is we want a certification protocol that kind of works for any target state. So we're going to assume inefficient classical computation. For example, our protocols will work even if the state psi is itself exponentially complicated. And then, let's think about what measurements are allowed. Well, if we have arbitrary measurements, then there's a very trivial way to do this, which is you simply do the two-outcome measurement that's projecting onto psi. But there's a lot of interest in doing the certification with much simpler measurements. So, for example, product measurements, by which I mean product on single qubits. So, of course, we have the trivial PBM, but it's difficult to implement. And we will only measure a few qubits at a time, ideally just 1 qubit at a time. The other thing we might want to have is little adaptivity. So especially in near-term devices, adaptivity is rather expensive. It's hard to hold on to a coherent post-measurement state. So it's great if the measurements are non-adaptive. And yeah, we would like the copy complexity of this task to be small. So notice that if we did have the trivial PVM pictured above, certainly you only need constantly many copies to do this, at least independent of n, many copies. And we want to hold on to that even in this world of having, very simple measurements. Okay, so there is there was like a breakthrough in this task a couple years ago by Huang, Preskill, and Soleimanifar, and I want to just describe the protocol because it'll be useful for describing our protocol later, and then also yeah, it just gets us thinking about these types of tasks. So here it is. It's very simple, not simple to analyze, but a simple protocol. So you have your lab state, so this mystery state row that you have copies of. You'll just randomly choose a qubit j to leave out, uniformly random. And then you'll measure all of the other qubits in the x basis. So simplest measurement you can imagine. You get some outcome, which is a bit string of length n-1, as well as a 1 qubit post-measurement state rho sub s. Then, you have in your mind this image of what psi you wanted. So you'll compute the post-selected target state as if you ran the experiment on psi itself. You get the post-selected target state psi sub s, same outcome. And again, this is a 1 qubit state. And you simply do the one-dimensional projective valued measurement on rho sub s. And you do some statistics on this. You run this experiment constantly many times. you do this, you do some statistics on it, and it gives you a way to certify things. Now this one was slightly adaptive, of course, because we had to compute the last measurement, but you can make it non-adaptive pretty easily. So this is exactly the same, but then instead of measuring the last qubit in this special 1-qubit basis, you simply measure row sub s in x, y, or z randomly, and then post-process. So this is, kind of in the theme of classical shadows, or these kind of Pauli-based measurements. XYZ is informationally complete for 1-qubit, et cetera, et cetera. Okay, so these are these basic protocols. Now, I want to talk about the actual performance that this protocol gets, as well as
Sorry,
performances. Yeah.
Sorry, if I can interrupt just very quickly to just get like the setting right. So at the very beginning, like, are you assuming anything like this row can even be like a mixed state, or are you assuming something besides that?
Row can be mixed.
Okay, and the psi is just like some given n-qubit pure state. And then okay, and then the second question. So like in the protocol you are describing, there's just like what is like on one copy, right? So you didn't say anything on like how many times you would need to repeat this to get like a good estimate.
Yeah, that's right. That's right.
Okay.
So actually for these protocols, you have to repeat them order n times in order to make it work.
Right.
For constant confidence. Yeah.
Right. And then in general, you only care about like the copy complexity, like how many such states you require. You don't care about like the time complexity of each of these steps, or do you also take this into account? Like you also want to have like time efficiency, let's say in n.
Yeah, that's a really, really important thing to keep in mind. So these protocols, at least the setup is that psi is arbitrarily complicated.
Right.
So, and once you have a protocol that you want to work for, uniformly over all psi, then you have to, of course, let go of computational efficiency.
Right. Okay, I see.
You absolutely can ask, in the case of subsets of psi, which are themselves efficiently describable, can I also get a computationally efficient test? This is an awesome question. There is one work I know of by Ulysse Charbot and collaborators, I'm sorry, I forget their names right now, that does this for things related to Clifford states, maybe literally Clifford states. But I think that's like a very meaningful next direction.
Right. So we don't have like a generic algorithm, but if I understand correctly, you would expect that the time complexity would scale with the size of the set from which we sample this state psi.
Roughly, yeah, roughly. I think, yeah. So certainly, if the description complexity of the state is larger than poly-n bits, then you're going to have problems. But it could also be that there are efficiently describable states where it's really unclear how to do this test computationally efficiently. Yeah. Yeah. There's a lot of mysteries about the computational complexity. I'd love to chat more about it. But yeah. So,
okay, that's great.
Thanks for your questions. Yeah. Yeah. So okay, so I described this kind of basic protocol, and so let's talk about how the performance is. So this is HPS 25. It uses single qubit measurements. Its copy complexity is order n, and you can ask, well, for what state psi does it work on? It actually does not work for all states, but it works for almost all states in the sense of if you take a hard random state and ask, does it work? It works with exponentially good probability. And then it's also non-adaptive, which is a nice thing for practice. Okay, but you may definitely want to get all states, like all states entirely. And this was resolved by this lovely work of Gupta, Hay, and O'Donnell in the most recent QIP. And they do get all states. Unfortunately, they need adaptivity. And moreover, they also prove that adaptivity is necessary if you want to get all states. So this is a very cool extra fact that if you have any non-adaptive algorithm, you can cook up a state that fails to be certified by this protocol. Okay, and maybe they don't use poly measurements, they use arbitrary measurements, but still it looks pretty good. But both of these protocols lack in something called robustness. And let me just say what robustness is. So the point is, normally when you're certifying states or something, the kind of most standard thing is you want to answer the question, am I equal to the thing I want to be, or am I far from it? A robust protocol instead says, am I close to the thing I want to be, or am I far? And so in the language of this talk, we'll say a T-robust algorithm is one that, can with high confidence determine the difference between being T times epsilon close and epsilon far. And epsilon can be chosen at runtime. T is usually a parameter of the algorithm design itself. So both of these protocols, what this robustness of 1 over n means, it means that as system size grows, the only time these protocols can be guaranteed to give a thumbs up is when the lab state is vanishingly close to the correct state. So if I'm like an experimentalist and I'm trying to make larger and larger quantum systems, in order to certify that the systems are correct using these protocols, as the system size grows, I also have to improve the accuracy of the system very, very quickly. And this is not always feasible in realistic experimental settings. And so it's very interesting to consider whether constant robustness is achievable. So for example, can I decide whether a state has, 80% fidelity with what it should be or 60%, something like this. Okay, so that brings us to the subject of this talk. So there's a paper out coming to stock this year that shows that for almost all states, you can get, well, okay, we give two protocols. One of them is single qubit measurements, where we have to be able to measure on any basis. Copy complexity is only logarithmic, and it works for almost all states, and it is adaptive, and it gets robustness 1 over log n. So this is an improvement over 1 over n. And then in the same paper, we give another protocol, which is not single qubit, it's log n qubit measurements. And it achieves constant copy complexity, works for almost all states, it's non-adaptive, and it has constant robustness. So yeah, I guess log n qubit Clifford measurements may be or may not be practical in near-term devices. But these two protocols kind of take us closer to the dream of having a robust state certification protocol. But they both have deficiencies. There's some logs floating around, which can be problematic. Let me also just mention that it's impossible to get all 5 columns green at the same time because of this result of GHO, that if you get it for all states, you cannot be adaptive. But it stands to reason that you can get all the other columns green simultaneously. So the thing I would like to talk about today is the kind of cleaning up of the previous work, where we remove the logs and we get all the columns green that we can. So this doesn't work for all states, but it is non-adaptive, and everything else is a constant, and you have very simple Pauli measurements. Yeah, yeah. A very enticing open question is, can we, essentially get all these things green, but allow adaptivity and get it for all states? I think that's a reasonable next question. Cool. Let's see what's next. Okay, yeah. Any questions at this point?
Yeah, maybe I can ask like two quick questions. So, do I understand correctly that already like your first result, the CLSW, the first protocol, already improves drastically over the first two entries, right? Because you improve both on the copy complexity and on the robustness, right? So that's already like a huge improvement. Because I was a bit surprised that somehow both the copy complexity and the robustness can be improved at the same time. I thought that there would be like some sort of like trade-off that if you want to improve.
Yeah, you know what's funny is that they kind of work hand in hand. So there's this phenomenon where if you're not very robust, then it tends to mean that you also need more copies to get the same level of confidence. To get constant, like if you're T robust, then you tend to need 1/T copies in order to get constant confidence. I don't think this is a theorem, but this is like typically what we see.
Oh, that's very interesting and very surprising to me. I see. And maybe like one other question about this. So in general, for like all these theorems, do you also have like statements that say, okay, if I want to only succeed, like either at telling exactly the state or even in the robust case with some probability p, then all this copy complexity are going to be a function of this p, or in general, you only care about like probability negligibly close to 1 or exactly 1?
Oh yeah. Right. So I'm hiding in this table, I'm hiding the confidence and the epsilon. So this robustness, of course, it's like epsilon versus T times epsilon. I don't remember off the top of my head what the dependence on delta and the confidence delta and accuracy epsilon are in the previous works. The copy complexity for us is it's simply 1/epsilon squared times log of 1/delta, which is actually the same copy complexity as the information theoretic optimal measurement, right, of just project onto psi. So we exactly meet the copy complexity of the best possible measurement.
Right. So you say 1/epsilon squared, there epsilon is the probability of your success.
Sorry. No. So probability of so like a confidence delta. So it's log of 1/delta.
Okay.
Times 1/epsilon squared, where epsilon is the accuracy.
Okay. I see. Okay, that's good. Thank you.
Of course. Thanks for your questions. Cool. Okay. So the protocol that I'll hopefully be saying some words about how to prove today, it's very similar to HPS, with a twist. Okay, so what we do is we have this holdout qubit J here, and in all the other qubits, we decide whether we'll measure in the X basis or the Z basis. So this is not a decision per qubit. This is like just saying, all but J, I'm either going to measure them all in X or I'm going to measure them all in Z. And then on qubit J, I'm going to measure it in X, Y, or Z. Okay, and then we simply measure them all in this basis. And then we get some outcome string, which is B for the what I'm calling bulk, which is probably not a helpful name here, and H for the holdout qubit. And okay, this post-processing, it's like this is roughly what's happening. The actual statistic that we use is a little bit more complicated than this. So think of this post-processing step as vaguely what's happening. It's not complicated. It's just not worth going into. The point is we simply do one measurement in this special Pauli basis, and then accept if like the results are what they should be. You can think of this roughly as repeating the non-adaptive protocol from HPS, but before you do their protocol, decide whether you're working in the Hadamard basis or not with probability 1/2.
Joe, can I ask a silly question? So here, how do you, okay, let me ask it in the following way. So if you had also Y when you're deciding the bulk basis,
Yeah.
does that not give you anything? Is it identical or is it hard to
Yeah,
analyze?
so it doesn't seem to give you anything.
I see.
Yeah.
And of course, if you remove it from the holdout qubit, it stops working, I guess, or we don't
That's right.
know.
That's right. Yeah. So you do need information
Theoretically complete.
theoretically complete on the last qubit. So it seems. But yeah, the rest, it's like you'll see it gets related to some uncertainty principle. And so we do need these two bases, but I don't think it will help to have more. Not a super meaningful way. Yeah. What's funny, I mean, I'll get to it at the end, but like I said, this protocol does not work for all states. It only works for 1 minus exponentially small fraction. And it's funny to imagine what are the states that are left out. Some of them can be rather simple. So yeah, things to think about. Okay. So like towards an analysis of this protocol, let me just mention that how in HBS there was this like slightly non-adaptive one that can be made non-adaptive. Similar here, and it's the slightly non-adaptive one that's a lot easier to analyze. So this is exactly as before. All I did instead of picking all these measurements, I computed that post-measurement state on qubit J instead and did the optimal measurement on that qubit. So it's exactly like HBS. I've just decided whether to measure the bulk of the qubits in X or Z. Okay, so
and that alone gives this exponential improvement.
Yeah. So it's one of these things where the protocol itself is very simple and a very simple modification of a previous protocol, but the analysis, this paper is not out yet. I hope to get it out in a month or so. The analysis is really complicated, and I'll try to do my best to explain the main ideas. So for the second protocol, the one that's like slightly non-adaptive, where we are doing this optimal measurement at the end, I can write down the probability of acceptance as follows. So this is 1/2 is saying either do this stuff in the X or in the Z, and it's it's kind of the natural thing, right? I've passed to pure states, so now we're in the special case that phi here we can imagine as our lab state. It's a pure state instead of rho. That reduction is it's kind of routine. And then this just means the post-measurement state on psi after measuring phi on all qubits except for I. It's exactly the protocol, okay? And the key lemma that's kind of the whole proof, this is the uncertainty principle. It says that for all but a negligible fraction of target states, for all other states phi, both of these expectations cannot be large unless phi has high overlap with psi. So let's absorb this. So this is the left-hand side is simply twice the probability of acceptance. And the right-hand side, the idea is if, let's say, phi and psi are orthogonal, then this thing is just bounded away from 2 by a constant. So it says that as long as psi and phi are orthogonal, one of these two expectations could be one. You could always, one of the bases, it could entirely hide the difference between phi and psi, but their sum cannot be 2. The sum has to be bounded away from 2. On the other hand, if phi were equal to psi, of course the sum will be 2. Okay, and I want to just connect this linear expression here with robustness. Okay, fine. So local global relation. Okay, so how does this relate to robustness? So the idea is you set up this picture, and this picture on the x-axis is the fidelity of phi and psi. Remember, phi is our lab state, and the point is we can lower bound the probability of acceptance just by the fidelity. This is some extra argument that's takes 2 lines to show. So the probability of acceptance is always at least the fidelity of phi and psi. And this uncertainty principle shows that the probability of acceptance is upper bounded by this line here, which is 1 minus c over 2. Now let's think about what's the robustness of the protocol. So the idea is, let's say we wanted to accept all states phi that have this much fidelity, that have fidelity at least, 0.9 with psi. Then we can draw this vertical line here. And what this tells us is that our probability of acceptance for this set of phi is at least, this much on the y-axis. So we draw a horizontal line. And what that means is if we can estimate the probability of acceptance, that means we know we can confidently reject any state whose fidelity is less than this edge here on the x-axis, like that, right? So now we get these 2 disjoint acceptance probability ranges here, and so we can reject all fidelities less than this and accept all fidelities more than that. Okay, so this is where you get robustness from this like linear function here. And so, yeah, kind of the whole analysis reduces to proving this uncertainty principle. Let me peek. Yeah, and of course we get no guarantees in the middle. Yes, okay. So let me just pause. Any questions about this uncertainty principle?
I still have some question. I'm still trying to digest kind of like the intuition that you were explaining a bit earlier. So do I understand correctly that somehow like your algorithm is kind of like a generalization of the one that you were showing at the very beginning, in the sense that now you're also considering like measuring this qubit J, and you measure it uniform at random between bases, and kind of like this this generalization, like measuring this qubit, is the one that gets you like this huge improvement.
Let's see. So the difference is like measuring the all but 1 qubit in a fixed basis, or measuring all but 1 qubit in one of 2 bases. Like that's the main difference.
Oh, sorry. Can you maybe then get one slide back to see again? But then also like this holdout qubit is measured independently.
Yeah. Oh yeah. We can go back one more. Yeah. Right. But this, I mean, this is the same as in the Huang, Preskill, Soleimanifar paper. The holdout qubit is measured in a random Pauli basis. This is the same.
Okay, I see. But I see. Okay. And now you are saying that you are using this separation between achieving 2 in the ideal case and achieving something less than 2 in any other case, to show this full separation.
That's right. So and actually we can talk about what happens in Huang, Preskill, Soleimanifar instead of this. So in there, they're not doing these two things with 1/2 probability each. They're only doing one of them. So you can imagine removing this thing from the left-hand side, and we're only focusing on here. What happens is that let's just focus on we'll see like a spectral formulation of what I'm about to say in a couple slides, but let's focus on phi being perpendicular to psi. Then, the question is like, how is that perpendicularity like kind of remembered by these 1-qubit post-measurement states? And the answer is like not so much. So if phi is perpendicular to psi, I can absolutely construct situations where this expectation here goes like 1 minus 1 over n. So instead of 1 minus a constant, it goes like 1 minus 1 over n. And this is exactly the source of the non-robustness. It just so happens when you average it with its, Hadamard transformed partner, instead of being 2 minus 2 over n, it becomes 2 minus a constant.
Oh, wow. I see. Okay, that's really cool. That's really cool.
Well, thank you so much for your interest. So it's okay. So now we're going to descend into deeper and deeper layers of mathematical confusion. So, well, hopefully not confusion. Okay. So like I was saying, yeah.
But before you go on, just one small thing. So I guess this is the place where you're just using X and Z, right? So if you added a Y, that would not buy you anything. But what would it appear as in this picture that you've drawn?
Yeah. So then, so in this green box, you would of course add another summand on the left-hand side, and then it would look like 3 minus a constant plus a constant times
But that part is already giving you a constant, so it doesn't buy you.
Yes, I mean the constant could be much better, and the constants are important. Like how I was saying, 60% fidelity versus 80% fidelity. The this little c here is exactly what's determining how much, how wide this gap is between reject and acceptance. So if you do improve the constant, it's not just a constant in the complexity theory standpoint. It's like really meaningful for practice. So yeah, it might be a better constant. I don't remember the numerical experiments, what they give. So yeah.
And
so
and sorry, just one small thing. So is it already clear why we miss out on some of the states in the Hilbert space from this picture, or is it better to look at it later?
Maybe better to look at it later. I can tell you already that certain product states are missed, which is kind of funny. Like somehow this protocol takes advantage of there being entanglement between different parts, different sites. So you can, I mean, already the paper that's out shows that there's like product states that are missed by this. I mean, but like this is a problem. So it's not that it completely fails to verify them, it's that it doesn't do it robustly.
So the intuition would be that if you somehow had, I should let you continue. I'll discuss later. But thanks. Yeah, that was helpful.
Sure. Yeah. So there's some states that it just completely fails to certify, and then there's other states that it certifies, but like not robustly anymore. So product states are in the latter category. Yeah. Thank you. Okay. So like we can talk about maybe a little bit why this theorem should be true. So now we're going to start from this expression, which is the special, you can reduce to the special case that phi is orthogonal to psi. And now we're going to convert this into the language of Boolean functions. In the natural way, we just write down, like ket x, like what's the coefficient on ket x as f of x here. So f will always and forever be the function associated with psi. G will always and forever be the function associated with phi, the lab state. And making this assignment, we can rewrite this uncertainty principle in this terrible way. So all I've done is I've rewritten the post-measurement states of psi and phi, the language of their Boolean functions. So this expression has a lot of symbols, but we'll spend the rest of the talk essentially looking at this expression, so don't be too worried. Yikes. Okay, maybe like one very basic thing is that both of these terms, they're summing over coordinates and summing over points. And then this summand, each of the summands, is some like average over edges. And over here, we're in the Fourier domain. So it's like sum over, Fourier edges. So I'm saying edges simply because we're always taking f with g at a point S, and then f with g at a point S plus ej. That simply means, move along an edge. So you can think of it as some quantity that's being measured over like all the edges of the cube plus the same quantity over all edges of the like Fourier cube. Okay. And we'll use some colors just to distinguish between f and g here. I want to give a kind of spectral formulation for this thing because it will help intuition. So I can rewrite this quantity here actually as a quadratic form in G. So of course there's denominators for f, and these are really unfortunate. But as a function of G, it's actually bilinear or quadratic. So I can define this matrix A sub f, okay? And then similarly, I can do this in the hat world. And if I do exactly the mirror symmetry thing over here, I get this expression. If I pull out the Fourier transform from the G's, then I can write it like this. Okay, and now I want to revisit this thing about your excellent question about the difference between HPS and this protocol. So in this, now that we have a matrix and we have some spectrum, remember G was the lab state. So one can show that with high probability over F, the target state, the spectrum of A sub F goes like 1 minus theta of 1 over n and smaller guys. So of course this is the eigenfunction for A sub F with eigenvalue 1 is F itself, right? And so once you start looking into the perpendicular part, you'll see that there exists, this is exactly what I was saying, there exists G, or there exist lab states, which are perpendicular to F, and yet their expectation, or this inner product, their energy with respect to A sub F is 1 minus, little o of n, sorry, little o of 1, and this is sad for the sake of robustness. And just by symmetry, the same thing holds individually for the spectrum of the Fourier transform version. And the whole point of this uncertainty principle is that the spectrum of the sum of these two matrices has a constant spectral gap. So this is very much like a standard, the standard kind of things you see in uncertainty principles. Yeah. Let's see. Atul, how much time do I have?
So we started at 8:30. So you have around guess in about 45 minutes, maybe 50, something like that.
Oh, okay. Okay. So yeah, well, okay. I don't want to, I don't want to put the listeners to sleep here. So maybe I'll just talk about the proof of a special case, and then we can fast forward to the conclusions and next steps. And then if people want to see how you extend from the special case, then we can go backwards. So, okay. So first, let's start with a toy version of proving this uncertainty principle. So I'm going to make the, fantastical assumption that every value of f and every value of f hat is positive 2 to the minus n. So there's no function with this feature. It does not exist, but let's just pretend it did. So if this is true, then what you can do is you can substitute it in. So I've simply, replaced all of these red things with 2 to the minus n. And the first term becomes something very familiar if you've studied the analysis of Boolean functions. So it becomes 1 over 4 times n times the average of, like the average of values at each edge squared. And if you do some rearrangement, it becomes 1 minus 1 over n, the kind of average difference between things on either edge. This is exactly the influence of a Boolean function. So in this fantasy world where our target state had associated function f, which is just a constant positive number, the expected outcome for the standard basis version is literally just 1 minus 1 over n times the influence, the total influence of this function g, which was the function associated with the lab state. And similarly, the second term, it's 1 minus 1 over n times the total influence of g hat, maybe unsurprisingly. And, in this fantasy land, if we still expect an uncertainty principle to hold, we would want something like, well, so it's we want a lower bound, right? Because we're writing these as 1 minus stuff. So we might expect an uncertainty principle like the total influence of g for any Boolean function, the total influence of g plus the total influence of g hat is lower bounded by a constant fraction of n. And it's a very simple statement, right? Because it's just about Boolean functions, by which I mean functions on the hypercube. They don't have to be Boolean valued. Very simple statement. But I couldn't find it in the literature. It only takes a couple lines to prove, and I just thought it's cute. So turns out that it's true, and you can prove it with sharp constant 1 minus 1 over square root of 2. So like our first, kind of sanity check works out in this very simple situation. We can get an uncertainty principle. So that's cool. And now, like but like I said, this is there's no such f with this feature. So let's try to think of the closest like actual f. And the closest actual f would be a phase state. Okay, so let's consider that f corresponds to a random phase state. And by phase state here, I mean the kind of broadest, in the broadest sense. So for each ket x in the standard basis, f of x is 2 to the minus n over 2 times a uniformly random point on the unit circle. So it's not a binary phase state. It's not a, FQ phase state. It's literally in each coordinate some complex number of uniform size. So we want to show that for almost all f of this kind, this uncertainty principle holds. Okay. So given what we saw in this fantasy version earlier, we might try to recover the total influence of G. So let's proceed down this path. The idea is to write G as f times Q. Why this would occur to you? Let's see. Do I have an explanation? I don't really have an explanation. It's just it just happens to work. So what we do is we're going to factor out a copy of f from G. And if we do this, then look what happens on the first term. So, So so some just little preparation. If we do factor out a copy of f from G, and to get Q, then note that G being normalized, which was just a property that's a state, is equivalent to Q being normalized with respect to the uniform distribution. So it kind of plays nicely there. And also remember that G and F were orthogonal because phi and psi were orthogonal. And this is the same thing as Q being balanced as a function. So its expectation is 0. Okay, so the point is if we factor out F to get a new function Q from G, it's still very well behaved in this very nice way. Okay, now look at this first term. What I've done is I've rewritten Q as F times G. Sorry, I've rewritten G as F times Q. And instead of having an F bar here, now it's the norm of F. So it completely forgets about the angle. Remember, F of X is some random angle, but now it completely forgets about it. And we exactly recover this, 1 over 2 to the n quantity, just like in the previous fantasy world. Okay, we're not working with G anymore, we're working with some other function Q, but maybe it's close enough. So we get exactly the same expression as before. Unfortunately, if you try to plug it in for the second term, it is seems to be inscrutable and terrible. So the point is like the hats don't commute with the substitution of G as F times Q. You can use the convolution theorem to like rewrite this thing, but it kind of, at least, it just leads to chaos. So it seems like making the substitution allows us to recover 1 minus the total influence in the standard basis, but it's unclear how to recover 1 minus total influence in the Hadamard basis. But undeterred, we can proceed in the following way. Let's do a win-win. So here's the general idea. Either the influence of Q here is large. So G has been turned into this Q, and the idea is either the total influence of Q is large, in which case the quantity on the left-hand side is bounded away from 1, therefore the whole thing is bounded away from 2, or the influence of Q is small. And the idea is maybe we can use the influence of Q being small to help us deal with this yucky second term. Okay, so if it's small, morally what this means is that Q is kind of low degree. And we know lots of stuff about low degree Q, low degree Boolean functions. In particular, we know that there aren't so many low influence functions. In particular, the size of an epsilon net of functions with bounded influence in this way, like a constant fraction of n, well, the point is that the epsilon net, okay, it's always going to be doubly exponential, but the constant in this next to n, the point is, it's not 2 to the 2 to the n, it's 2 to the 2 to the c times n for some constant. And we get to set this threshold little c, so we can make it 2 to the 2 to the constant times n for a constant of our choosing. And although this seems like not much, it actually is exactly what's needed to finish the argument. So, yeah, so this nearing the end of this phase state proof here. So what's the general argument? So the first thing to say is that, so let's repeat the win-win. So if the influence of Q is large, then this first term, remember it's G a sub fg, this first quantity, measurement in the x basis, is bounded away from 1, and we're done. The reason is the sum of these two guys is bounded away from 2 by a constant. Otherwise, the influence is small. And it turns out, so now we make this epsilon net type argument. So it turns out that, okay, let's imagine doing something weird for a second. We're going to fix a Q and consider the randomness over F. Recall that the actual order of quantifiers are different, right? We want to say for a random F for all Q. Let's pretend we're saying for all Q for a random F for a second. So it turns out that for a fixed Q, the second term here, the terrible term with the hats, the expected value over F is 1/2. Moreover, you can show with great effort that this term also concentrates. So the probability that it's larger than, for example, 0.51 is just fantastically small, vanishingly small. And so by a union bound, there is a very fine net of these low influence functions so that the probability over random f for all q in this net, the quantity of interest is larger than 0.51, is small. So we simply union bounded this part up here with the number of q in the net. And because we got to choose C ourselves, we can ensure that the size of the net, the cardinality of the net, is smaller than this concentration tail. And so we get that with high probability over F, for every Q in this net, this thing is very, very close to 1/2. Remember, we only needed it bounded away from 1 by a constant. We get something much better. We get it very close to 1/2. And because it's true, because this thing holds with high probability over F for every Q in a net, and the net is like fine, we can just use like continuity to say we can pass from the net over special Qs to the net over all Q, sorry, to the set of all Qs simply by, smoothness or Lipschitzness of this map. And so we get now that with high probability over F for all Q at all, the second inner product is at most 0.52, which is, even more than we needed. So, yeah, so essentially we couldn't directly handle the Fourier side of the expression, and instead we did a win-win and some probability theory to make it work. I'll mention that this thing is like rather arduous to prove because like the quantity is rational, so there were those denominators, and this makes concentration quite tricky, but we made it work. So yeah, just to reinforce this win-win idea, this is the general thing. So either influence is above a threshold, in which case we have bounded away from 2, or it's below a threshold, in which case we have something even stronger. Okay, and that concludes the proof for phase states, for a random phase state. Yeah, so then the general case is like that new monsters emerge in the general case. I will not go into it too much. What is the main idea? Yeah, I guess right. So the main idea, the thing that breaks in the general case is that, we had this win-win, right? Where we said either the influence, we factor out a Q and we say either the influence of Q is large, in which case we're done already, or it's small, in which case we can control this epsilon net and make this argument. Unfortunately, in the case where an F is not a uniform phase state, like of coefficients of uniform magnitude, it's not true that the influence of Q bounds the cardinality of an epsilon net. It's just simply not true anymore. And so you end up having to like split the domain, you split the hypercube into like a good part and a bad part, and repeat the earlier argument on the good part of the cube and do something different on the bad part of the cube. And I'm happy to explain why and how and so on and so forth. But I'll skip this for now and just say, the argument, after some more work, can be essentially extended. Okay. But let's just finish up here and conclude. So I think there's a lot of interesting.
Joe, before you start, just to quickly understand, so you looked at special cases, right? Special kinds of states. and for which you could sort of argue. So this much I could follow. But then when you go to a general state, are you
Yeah.
sampling from some distribution and then making some kind of argument?
Oh, sorry.
Or
Yeah.
is
So
it
the theorem is that this uncertainty principle holds with high probability over a Haar random state.
okay. So then you want to show that for the Haar distribution of states that this analysis goes through, and that's where the this influence argument needs to be sharpened, and it doesn't go as it is.
Yeah.
Is
Yeah,
the
that's right.
file. Okay. Thank you.
Of course. Hmm. Okay. Yeah. Sorry, I should have said that. Yeah. So, right. So this proves that almost all states in like Haar, almost all states can be robustly tested with this uncertainty principle that, is a difficult mathematical statement. But there's a lot still to be done. So here's some mysteries. How about hay from the haystack? So can we characterize large classes of states which are entirely contained in the good set for this test? These, have you heard of bent Boolean functions? They're like these special things that, they're Boolean functions whose coefficients, so they're Boolean valued. And then when you take the Fourier transform, they're still Boolean valued. Like they're, in general, Fourier coefficients are not all of the same magnitude, but bent Boolean functions do have this feature. So there's a special subclass of bent Boolean functions, which is some example from hay from the haystack. Fortunately, it's not a very natural class, so it'd be nice to get some natural classes that fit inside here. Of course, the one really exciting thing here is to robustly test all states. So you do need adaptivity. The other thing is you can kind of argue all of the protocols in the literature so far. What do? They do a bunch of measurements, and then they, maybe future measurements depend on the previous measurements. But then the actual decision bit of like whether we accept or not this state, it actually is just a function of the last qubits measurement. And you can prove that any protocol of this kind cannot robustly test all states. It's a short argument. It's in the paper that's out already. So you need, if you want to robustly test all states, you need an idea beyond just deciding as a function of the last qubit. Yeah, the other thing that would be nice is the proof that I started to sketch in this talk. It gets, remember, the uncertainty principle is like blah, blah, blah is at most 2 minus C plus other stuff. That C in the proof is implicit. Like it's not a good C. It's not like, it's going to be some absolutely tiny number that's embarrassing to write down. But numerically, the C should be kind of big. So what is this plot of? This plot is as the number of qubits grows, take a Haar random state and just figure out, what's the maximum acceptance probability times 2. And it seems to be decaying. It seems to, like in experiments, it seems to settle around 0.16 instead of 2. So that's like a very good constant. And it would be nice if there's a different argument which can prove this much better constant. Right. So the argument that was given shows that the middle of each violin plot is, at most 1.999999. Yeah. So maybe there's some other argument, maybe via Brownian motion. The other thing that would be really nice is, our test, you can call it robust, but it's not tolerant. So fully tolerant testing, we can do, epsilon close versus C times epsilon far, but you can't adjust both sides of this window individually. So a fully tolerant tester would allow you to say, I want to distinguish things that are epsilon 1 close versus epsilon 2 far, and my copy complexity and everything else of my protocol should be a function of epsilon1 and epsilon2. And these are completely independent numbers. And yeah, we don't have a way to do that. And it doesn't seem like an uncertainty principle suffices. So I think that's also a really nice question. It's just a lot of notation. Let's see if there's anything intelligent to say. So did this epsilon net argument make sense?
At a high level, I mean, I did not follow all the equations, but yeah, at a high level, I could see how this might work. Yeah.
Yeah, like the whole thing is about quantifier switching,
Mhm.
right? Like
Mhm.
we had to prove something with high probability over f that for all q something happened, but we don't know how to think about that. So instead, what we say is for all q, it behaves well with high probability over f.
Mhm.
And then there's this lovely trick of how can you switch the quantifiers? Well, you can do this if the good event happens with like fantastically good probability. Because if for any fixed q, the good event happens with fantastically high probability, then that means for many q, it happens simultaneously. And if that's true for enough q, you can fill out the entire world of q's by these good q's.
Mhm.
And then this allows you essentially to switch your quantifiers. Yeah, and unfortunately that win-win, that kind of epsilon net argument doesn't go through immediately in the general case because we don't have control over the epsilon net size in the general case. And the reason is that in general, you know how when we switched from F to Q, sorry, from G to Q in the phase state version, we got like Q was like balanced and behaving well with respect to the uniform measure. In the general case, when we switch from G to Q, it's no longer, sorry, it should be written somewhere. It's no longer with respect to the uniform measure. So here, I'm still plugging in G equals F times Q. So now F is a Haar random thing, but G equals F times Q. And we know that G is normalized if and only if Q is normalized not with respect to the uniform measure, but with respect to a measure defined by F. When F was a phase state, this always gave you the uniform measure. No longer true. It's this Porter-Thomas thing. Similarly, F perpendicular to G turns into Q being balanced not with respect to the uniform measure, but with respect to this measure defined by F. And the problem is that even though Porter-Thomas is like kind of uniform, it's not uniform enough. So there are certain points X where mu is like extremely tiny, and then other points where it's slightly larger than it should be. And this fact prevents us from making these naive epsilon net arguments. So in particular, you can find in the cube, when you get this measure mu, you can find bad points where you can like hide a large number of different q's. Essentially, yeah, you can prove that low influence q in this general picture, there are too many points. There are too many functions q of low influence. And so what you end up doing is you take your cube and you split the points of the cube into two sets. The good set, which is green here, so this is just a matrix where the rows and columns are labeled by points on the hypercube. And in the green box, this corresponds to points where the measure of x, the measure mu, right, defined by f, it's this Porter-Thomas thing, the measure mu is like roughly uniform. And when it's roughly uniform, this is some, unstructured subset of the cube. When it's roughly uniform, then you can repeat the argument. And so the rest of the labor in this paper is handling this yucky other thing. And yeah, you have to handle it in different ways for different parts. Yeah, but yeah, it takes some more ideas. You have to get some operator norm concentration, and you have to compare like the influence just on this subspace to the influence of Q itself, and we actually end up we got some inspiration from the technical analysis in the HPS paper to like do some like pathwise analysis to make it all work. But
So
yeah.
that paper did not use Fourier. I think he used, or was that also?
It didn't use much. No, I don't think so. I think HPS was like entirely these random walks on a cube kind of thing, because there was no Fourier basis in HPS.
Right, it makes sense, of course. Yeah, I see. That is interesting. Okay.
Yeah, so yeah, it was definitely like a whack-a-mole thing. Like we got something that worked, and then okay, it broke in the other thing, so we whacked that mole, and then another mole appears, and
Right.
there ended up being 3 moles, but then no
Right.
more.
Right.
Yeah, thanks for the opportunity to chat about it.